Let's start today's digital electronics class. In the previous lecture, we covered the basic operation of different types of flip-flops. Today, we will continue with the advanced feature of the flip-flops that we covered so far. First, we'll discuss about the preset and clear inputs for the flip-flop. Here in this slide, we can see the logic diagram of SR flip-flop that was covered in the previous classes. For SR flip-flop and JK flip-flop, the SR inputs and JK inputs for JK flip-flop and SR inputs for SR inputs are called synchronous inputs because data of these inputs are transferred to the flip-flop's output only on the triggering edge of the clock pulse. That is, the data are transferred synchronously with the clock. Most integrated circuit flip-flops also have asynchronous inputs. These are inputs that affect the state of the flip-flop independent of the clock. That means they are inputs for which the outputs will not depend on the clock pulse. They are normally labeled preset and clear, or sometimes they are represented by direct set or direct reset. But most commonly they are represented by preset and clear input. Here in this SR flip-flop, we'll add two more inputs which will represent preset and clear inputs for this particular flip-flop. We can see we are going to add one input here that is represented by preset input. This input is represented by a bar, which means this is active low input. Again, to have our clear input, we'll take one input from here, and clear is having also a bar. That means it is also active low input. What are the functions of this preset and clear inputs? As I told you earlier, that this input, preset input and clear input, they do not depend on the clock pulse. Rather, whatever the clock pulse or set or R value, whenever preset is activated, the output will be set. When the clear is activated, the output will be cleared. That means reset. And these inputs are independent of clock pulse. That means they do not depend on clock pulse. Let me tell you the operation. Whenever preset is activated, the value of preset is given 0. It's active low input. Active low input means it will be activated when the low input is given. Low input means 0 input is given. Whenever 0 input is given, one of the input of this NAND gate is 0. So what will happen? The definite output will be 1. Whether clock pulse triggers or not, the output will be set to 1. That means the output is set. So we are setting the output beforehand. That's why it's called preset. Again, when the clear input is activated, which means we are giving 0 input at clear, keeping preset equal to 1, 0 input at clear. So one of the input here will be 0. So if I have one of the inputs of this NAND gate is 0, so what is the definite output of Q prime? Q prime will be 1. If Q prime is 1, we have 1 here, preset equal to 1 here, and as clock pulse input is 0, or we are not considering this input, so these inputs can be taken as 0 input. So the definite output will be 1 here. So 1, 1, 1 will make the output Q equal to 0. Q equal to 0 means the output is cleared or output is reset, 0 output. So in this way, forcibly, without depending on clock pulse or inputs, we can set our output Q equal to 1 or Q equal to 0 by activating this clear input or preset input. Things will be more clear if we see one timeline diagram. This is the graphical symbol for SR flip-flop with preset and clear input. Inside this box, we have this logic diagram. Now let's draw a timeline diagram for D flip-flop with preset and clear input. This is the graphical symbol for D flip-flop. We have preset input, which is active low input, and clear input, that's also active low input. the clock pulse input is given here, preset input is given here, clear input is given here, D input is given here. We need to plot the Q output for this case. Now, as we can see, this is positive edge triggered D flip-flop. So let's mark the positive edges for all clock pulses. These are the positive edges. This is the point where the state will be changed. Now, initially, what is the value of Q? We can see the value of preset is 0 and the clear value is 1. Clear value is 1 means clear is not activated, rather preset is activated because they are active low. As preset is 0, so the preset value is activated. When preset is activated, what will be the output? Output doesn't depend on clock pulse or D input, rather the output will be forcibly 1. Up to which time? Up to this time here, up to this amount of time, the output will remain 1. After that, from this time to next clock pulse triggering, as we have preset equal to 1, clear equal to 1, so preset is deactivated, clear is deactivated, so it will have a function like simple D flip-flop. In D flip-flop, when clock pulse equal to 0, we do not care about input, it will hold the previous. So from here to here, this value will be 1 because we have preset activated, and here to here we will have 1 because it will hold the previous. The line will be like this. Now, when this clock pulse triggers, at this moment, at this triggering moment, preset is 1, so preset is not activated. Clear is 1, clear is not activated. D is 0, so the output will be 0 because this D output will be propagated to the next Q output side. Next, from here to here, within this period of time, it will follow the previous output. As during this period of time, we have clear equal to 1, preset equal to 1. We need to check when the clear and preset is equal to 0, then we do not have to bother about clock pulse or other D input or other inputs. Preset and clear will dominate the outputs. But when preset and clear both are 1, then the flip-flop will act as normal D flip-flop. From here to here, we have preset equal to 1, clear equal to 1, so that they are deactivated. So from here to here, once we get this clock pulse triggering, in this clock pulse triggering we are getting D equal to 1, so D flip-flop will be set. It will get the 1 value. And from here to here, as long as preset and clear are, both are 1, so it will follow the previous. Here, while triggering again, while triggering the clock pulse, we see preset and clock clear both are 1, so we don't have to bother about that. It will follow the inputs. What is my input? The D input is 0, so it will go back to 0. Again, during this period of time, let's check what we have. We have preset and clear equal to 1, so they are deactivated, so it will follow the previous up to this timing. In the next clock pulse triggering, what we have? We have preset equal to 1, clear equal to 1, D value is equal to 1. So in this triggering point, the output will go to the 1 position again. Now we need to check. This clear value goes from 1 to 0 at this moment. This is a time between two positive edge triggering. So at this moment, this clear comes from 1 to 0. When clear comes from 1 to 0, that means clear is having 0 value. 0 value means clear is activated. So at this line, we do not care about what is my clock pulse, what is my D input. The output will be forcibly brought back to 0 position. And as long as clear is 0, the output will have the 0 value continuously. This is the logic diagram of JK flip-flop with preset and clear input. The operation is similar to that RS flip-flop case with preset and clear input. This is the graphical symbol for JK flip-flop with preset and clear input. Inside this box we have this logic diagram. Next we will cover master-slave flip-flop. Before I start that topic, let me tell you why do you need to implement master-slave flip-flop. This is the typical logic diagram for JK flip-flop with pulse transition detector. What will happen if we do not use pulse transition detector after the clock pulse signal? Suppose we have a clock pulse signal and we are not using pulse transition detector. So it's level triggered JK flip-flop. For clock pulse 0, it will hold the previous. For clock pulse 1, for input JK equal to 0, 0, it will hold the previous 0, 1, reset, 1, 0, set. But when clock pulse equal to 1, remember I am talking about level triggering, because here we are not using pulse transition detector. So we are talking about level triggering. So when clock pulse is 1, if we provide j equal to 1, k equal to 1, then it will toggle the previous q prime t. So this is the case where the problem will occur if it's level triggering. What will happen? The clock pulse will be 1 for a longer period of time. As long as clock pulse equal to 1 and j equal to 1 and k equal to 1, first if the previous value of q was 0, then it will go to toggle value, that means 1 value. Again, as 1 1 input is still there, that 1 will go back to 0 because it will toggle the previous. Again 0 will go back to 1. Again 1 will go back to 0. Now, this changing will be continued as long as clock pulse equal to 1. If we see the timeline diagram when j equal to 1, k equal to 1, what will happen during this period when clock pulse equal to 0, we are assuming initial value of q is 0, so it will hold the previous, no problem. But when clock pulse triggers and goes to 1, as it is level triggering, first of all, due to j and k both are equal to 1, it will toggle the previous value was 0, so it will go to 1 value. Again, as 1 1 is still there and we have level triggering, this 1 will come back to 0. Again, that means toggle, it will toggle the previous value. Again, this 0 will go to 1 and 1 will come back to 0. 0 will go to 1, 1 and come back to 0. This will keep continuing during the clock pulse 1 period. But when we have clock pulse equal to 0, again it will hold the previous value. Now if it finishes at 1 value, then 1 will continue. If it finishes at 0 value, 0 will continue up to here. So we are considering, suppose it was finished at 0 value and 0 will continue up to here. Again when clock pulse triggers, this 0 will be toggled because still j, k are 1 1. So what will happen? This will happen 1, and when 1 goes there at q output, then as long as the clock pulse equal to 1, it will toggle, and again a 0 will go to 1. It will be toggled in this way. It will produce a shape like this, high frequency signal, and also will have this type of high frequency signal here. This frequency depends on the response time of each gate. This phenomenon is named as race around condition, which is not expected output from a flip-flop. This is not a stable output, this is an unstable out. It keeps changing. How can we get rid of this condition? First of all, one of the methods that we already followed, that is, we used edge-triggered flip-flop. Edge-triggered means that there is a pulse transition detector. So when clock pulse triggers, when clock pulse goes from 0 to 1 for very small amount of time, timing of the triggering is less than our logic gate response time. That's why when it triggers, at that moment, if I have j equal to 1, k equal to 1, it will toggle the previous value. And after triggering, though I have level here, clock pulse equal to 1, but that trigger output will be 0. So that previous value will continue up to next triggering. So in this way, we will get the toggled operation from JK flip-flop. Another way for solving this problem is to use master-slave flip-flop. This is the basic block diagram of master-slave SR flip-flop. We have two SR flip-flop here. One is here and another is here. The output of the first SR flip-flop is connected with the input of the second SR flip-flop. Both the clock pulses are connected from a same source, but first one is connected directly and second one is connected through a NOT gate. This first flip-flop is termed as master flip-flop and the second flip-flop is termed as slave flip-flop. How it operates: when we give clock pulse signal equal to 1, as we can see, both the flip-flops are level triggered flip-flop. When the clock pulse signal is 1, this flip-flop, the master flip-flop, is activated. When clock pulse equal to 1, if we give set input, the set input will be transferred to the output of the master flip-flop. But when clock pulse is equal to 1, due to this inverter, the input for the slave clock pulse is 0. So even though we have output available at the master side, this output will be available at the input of the slave side, but as clock pulse is equal to 0, this input will not be transferred to the Q2 side. When clock pulse goes from 1 to 0, during this period, the 0 input will be available in the master clock pulse signal. However, whenever we have 0 here, due to this inverter, slave clock pulse will get 1 in the clock pulse input. So whatever input data we have here, that will be transferred to the Q2 side. So we can say when the clock pulse is 1, master is activated, slave is deactivated. When clock pulse is 0, master is deactivated, slave is activated. So to transfer data from this side, from the input side to the ultimate output side, first when clock pulse goes from 0 to 1, and during this period of time, data will be transferred from the input side to the intermediate position. Then when clock pulse is 0, during this time, the data will be transferred from this intermediate position to the final output position. This is the logic diagram for master slave JK flip-flop. We have master portion is here and slave portion is here. Both master and slaves are connected with same clock pulse triggering, but the first one is having the direct connection, second one is having a connection through this NOT gate. Now, when j equal to 0, k equal to 0, j equal to 1, k equal to 0, j equal to 0, k equal to 1, the operations are similar to our master slave RS flip-flop. That's why I'm not going to describe it here. But when we have j equal to 1, k equal to 1, what will happen? Suppose j equal to 1 and k is equal to 1 and clock pulse is 1. We are having the level triggering. Here we are not using pulse transition detector. So we are having the level triggering. During this on period of time, this master flip-flop will be activated. So any input change will cause the change in output of the master. So for example, we have clock pulse equal to 1. During this 1 time, we are getting j equal to 1 and k equal to 1, and this j and k both are having a feedback from q and q prime. Q prime is connected near to the j and q is connected near to k. So both of them are having feedback from q and q prime. As cp equal to 1, j equal to 1 and q equal to 1, the output of the master flip-flop will be the toggle value of this previous output of the slave flip-flop. Now, as long as this clock pulse is 1, even though this master output is toggled, this toggled output will not affect the slave flip-flop, because clock pulse 1 means slave flip-flop is getting clock pulse is equal to 0. When clock pulse is equal to 0, it's holding the previous value. So this output will not cause any change in this ultimate output. When clock pulse comes back from 1 to 0, so what's happening? this master will be deactivated. The slave will be activated, because when clock pulse is equal to 0, then the clock pulse for the slave input will automatically become 1 because of this inverter. So when it's 1, the available inputs that was previously available during the on time of this clock pulse from the master side, they will change the output of the slave side. So during this time, they will change the output of the slave side. Now, when it changes the output of this slave side, this output will come to the master side as feedback at that instant. But as long as this clock pulse is 0, this feedback will not cause any problem in the output of the master side, because during this CP0 time, this master is deactivated. Again, when clock pulse comes from 0 to 1, this master is activated, and we have the feedback from the previous clock pulse. We have the feedback. Based on that feedback, if we have JK input, again that will be toggled. So you see, this toggled is stored here for one half of the total clock pulse period. In the next half of the total clock pulse period, this data is transferred to the ultimate output side. That's why it's not causing that race around condition problem, or that high frequency unstable condition problem that we faced when we used only one single JK flip-flop having level triggered clock pulse signal. In this way, we can have the normal operation of JK flip-flop by employing master slave JK flip-flop. Let us see an example when we employ master slave JK flip-flop and level triggered clock pulse. Suppose we have initial previous value is 1, Q equal to 1 and Q prime is equal to 0 for 1 input and level triggered clock pulse. What will happen when clock pulse is equal to 1? This master flip-flop is activated. So in this master flip-flop, when we have J equal to 1 and K equal to 1, the output of this master flip-flop will be the toggled of the previous value. What is my previous value? Q equal to 1 and Q prime is equal to 0. They are coming as feedback to this J side and K side. So when we have J equal to 1 and K equal to 1, at this output side of the master flip-flop will get 0 and 1, the toggled output of this previous value. Now these 0 and 1s are available at the input side of the slave flip-flop, but they are not allowed to be transferred to the output side as long as clock pulse equal to 1. Now when clock pulse goes to 0 during this period, what will happen? During this period, this master is deactivated and slave is activated, because clock pulse 0 means here for the slave will get clock pulse equal to 1. So when clock pulse is equal to 1 for slave case, what's happening? We are giving 0 at the J side and 1 is in the K side. So what will be the output? The output will be reset. When the output is reset, we'll get 0 here and 1 here. We can see when the clock pulse is 0, this data given an output Q equal to 0 and Q prime equal to 1, which is the toggle version of the previous output. However, these outputs are available as feedback to the master side, but this output will not affect the output of the master flip-flop as long as the clock pulse is equal to 0, because clock pulse is equal to 0 means this master flip-flop is deactivated. Now again, when clock pulse goes from 0 to 1, during this on time, what will happen? As still we have J equal to 1, K equal to 1, and that feedback is coming 0 and 1. So this master flip-flop will toggle our previous output. So what was the previous output? That was 0 and 1. So here it will be 1, 0. Again, during this on time, this 1, 0 input will not affect the slave output, because during this on time, this clock pulse is 0. When clock pulse comes back to 0 position, what will happen? Master will be deactivated, slave is activated. So slave is getting 1 here and 0 here, 1 in the J side, 0 in the K side. So this is the set case. So what will be the output of the set output of the slave during this 0 time? We'll get 1 and 0. This is the set output. So again it's toggling the previous output. So we are getting the toggled output after each complete clock pulse. In half clock pulse, the data is transferred to the master, and in the next half clock pulse, that means during the off time, the data is transferred through the slave side, and it's giving us a stable toggled output for each clock pulse. Till now we have got the ideas on different types of flip-flop. Next, we'll start designing our sequential logic circuit. The logic diagram of a sequential circuit consists of flip-flops and usually combinational logic gates. Here in this slide, we can see the typical block diagram of a sequential circuit. In order to design the sequential circuit, we need to know the block diagrams so that the designing procedures become a bit easier. First of all, there will be a set of flip-flops, and these flip-flops will take input from the combinational logic circuits. We may have n number of inputs and n number of outputs. These are the inputs of flip-flops. Inside this box, a number of flip-flops will be used. All the flip-flops will be triggered by clock pulse. The flip-flop state output will be here. We have a number of outputs, and from the outputs we may take feedback to the combinational logic circuit. There will be input and there will be output Y. For the time being, I want all of you to learn about the block diagram. Things will be more clear when we'll design a sequential circuit. In order to know how to design sequential circuit, we need to have knowledge on state table and state diagram. We will start learning about state table first. The functional relationships among the inputs, outputs, and flip-flop states of a sequential circuit can be represented in a state table. It will be easier for us to learn about state table and state diagram if we proceed with sequential circuit design with an example problem. Let's have an example problem. Design a 2-bit up counter. I'm coming to the point, what is 2-bit up counter, with an input X and an output Y, which will keep counting with output value Y equal to 0 if input X is equal to 0. When the input X is set to 1, the counter must pause at the current value and Y will be 1. This is a sequential circuit designing problem. It is asked to design a 2-bit up counter. What is 2-bit up counter? This is a counter which will consist 2-bit. That means A0, A1, for example. So it will have 2-bit A0, A1. So maximum 4 states can be found: 0, 0, 0, 1, 1, 0, 1, 1. As it's saying up counter, so it will start from 0, 0, then it will go to 0, 1, next it will go to 1, 0, next it will go to 1, 1. When it reaches the maximum point, again it will come back to 0, 0, 0, 1, 1, 0, 1, 1. In this way, it will count. With an input X and output Y, things will be a bit easier if we draw the block diagram. This is the block diagram for this problem case. We need to design this box, sequential logic circuit. We have the sequential output A0 and A1. Why am I taking A0 and A1? Because it is said it should have 2-bit. So 2-bit up counter A0, A1. So it will count starting from 0, 0, then 0, 1, 1, 0, 1, 1. With an input X, we must have input X and output Y. Now, what is the function? Which will keep counting. It will keep counting with output value Y equal to 0. When it will count, output value will be 0. if input is set to 0. So if input is 0, then the count, it will keep counting, and output that will be shown here will be 0. There is a clock pulse. So in every clock pulse triggering, this counter will change its states. First triggering, it's 0 0. Second triggering, it's 0 1. Third triggering, 1 0. Fourth triggering, 1 1. Again, fifth triggering, it will come back to 0 0. In this way, it will keep counting. When the input is 1, this is the user defined input. When user will give an input which has a value 1, the counter will stop there. Suppose it was counting 0 0 0 1. At that moment, we give input equal to 1, it will stop there at 0 1 point, and the output should show 1. One thing we must remember, inside this box what we have the same block diagram that was shown in the previous slides, like this. This is combination logic, this is flip-flops, and combinedly we have this inside that box. We have input, we have output, we have sequential output. We took A0 and A1 only for our example case. So inside that smaller box, we have that bigger blocks. Now state table. In a state table, there are some columns. We need to have present state, input, next state, and output. So these will be represented in a state table. How can we express? So we must have present state, input, next state, output. Let's start drawing the state table based on the problem that I showed you in the previous slide. First of all, if my state will have 2-bit value, because it is said in the question that we need to design a 2-bit up counter. So the state will have 2-bit value. If the present state can be represented by A0, A1, input X, next state will also be A0, A1. Now let's see the first case. If the present state is 0 0, and the input is 0, what will be the next state? In the question, it was said that we need to design up counter. When input equal to 0, it will keep counting. So if the present state is 0 0 and input is 0, that means it must keep counting. The next state must go from 0 0 to 0 1. Then in the next triggering, if the present state is 0 0, the next state will be 0 1. And when it goes to 0 1 value, the output must show 0. Now, if the present state is 0 0, but input is 1, what will be the next state? We said that the circuit must pause. That means if the present state is 0 0, but input is 1, it must pause at 0 0. So the next state will also be 0 0, and output will show this 1 value. Next, if the present state is 0 1 and the input is 0, means the circuit will be running. We are giving input equal to 0 and the present state is 0 1. What will be the next state? We are designing up counter. The next state will be 1 0. So if we have input 0, it will keep counting. The next step will be 1 0 and the output will be 0. But if the present state is 0 1 but the input is 1, when the present state is 0 1 and the input is 1, whenever we will give input equal to 1, this state must pause. So what will be the next state? If the present state is 0 1, if we want to apply the pause situation, the next state will also be 0 1. So it's not changing its state because of giving this input 1, and we must show output for pause case. Whenever we have input equal to 1 0, for 0 case, it will go to the next state 1 1 and it must show 0 output. Whenever we have 1 0 in present state but input is 1, it will be paused. That means 1 0 will prevail and the output will be 1. Whenever we have present state 1 1, once it reaches to 1 1 value, what will be the next state? if input equal to 0, it will keep counting. After 1 1, when it reaches to the maximum value, it will go back to the 0 value. So from 1 1, if the input is 0, it will go back to 0 0. Next state will be 0 0, output will be 0 here. If the present state is 1 1 but input is 1, it will be paused. That means 1 1 will prevail. So 1 1 will be there and the output will be 1 here. So this is the state table for the problem that I showed you in the previous slide. The information available in a state table may be represented graphically in the form of a state diagram. Now we will learn how to produce a state diagram from a state table. Suppose this state table is given. In the state variable, how many bits are there or how many variables are there? There are 2 variables. Now using 2 state variable, how many distinct state can we have? We can have 4 distinct states, 0 0, 0 1, 1 0, 1 1. When we'll draw the state diagram, first of all we must represent that 4 distinct or maximum number of distinct state using or that particular number of state bits. So we have here 2 bit. So using 2 bit we can have 4 state, that is 0 0, 0 1, 1 0, 1 1. Now first of all, when we have 0 0 as present state, if we give x equal to, that means input equal to 0, the next state will be 0 1 and the output will be 0. So how is it represented? If we have present state 0 0, the next state will be 0 1. So from 0 0 we need to go to the next state 0 1 if input x equal to 0. Hence we will draw a straight line from 0 0 to 0 1 and we will write x by y. The left side represent the input part and the right side represent the output part. So what does this mean? Whenever the present state is 0 0, it will go to the next state 0 1 if the input x is equal to 0. If it goes to the from 0 0 to 0 1, then output will be 0. It means like this. Let us go for the next one. If the present state is 0 0, input is 1, then the next state will be 0 0 and the output will be 1. How is it represented? If the present state is 0 0, if the input is 1, the next state will also be 0 0 and the output will be 1. How can we represent that? We will represent that if the present state is 0 0, the next state will be 0 0 if the input is 1, and that condition output will be 1. So this line has been represented graphically. Next, if the present state is 0 1, if the input is 0, next state will be 1 0. So if the present state is 0 1, the next state will be 1 0 if the input is 0 and at that moment output will be 0. If the present state is 0 1, input is 1, the next state will be 0 1. If the present state is 0 1, if the input is 1, then the next state will be 0 1 and the output will be 1. In this way we represent our state diagram from state table. If the present state is 1 0, input is 0, next state will be 1 1. If the present state is 1 0, next state will be 1 1 if the input is 0 and the output will be 0 in this case. Again, if the present state is 1 0 and the input is 1, the next state will be 1 0 itself. If the present state is 1 0, the next state will be 1 0 if the input is 1 and the output is 1. If the present state is 1 1 and the input is 0, the next state will be 0 0. How is it represented? If the present state is 1 1, next state will be 0 0 if the input is 0 and the output will be 0. If the present state is 1 1, next state will be 1 1 if the input is 1 and the corresponding output will be 1. If the present state is 1 1, next state will be 1 1 again if the input is 1 and the output will be 1. In this way, from state diagram we can reproduce state table. I hope all of you understood, and now you will be able to reproduce the state table from the state diagram. For example, if you are asked to produce state table, I hope you will be able to do that. We know from the state table, if the present state is 0, 0, if the input is 0, the next state will be 0, 1. If the input is 1, the next state will be 0, 0. And the corresponding output will be 1. Again, if the present state is 0, 1, so we'll write 0, 1 at the present state. If the input is 0, the next state we find that it's 1, 0, we'll write 1, 0 here, and the corresponding output will be 0. Again, if the present state is 0, 1, here if the input is 1, it comes back to 0, 1. So if the input is 1, the next state will also be 0, 1, and the output is written here, we'll write output here. In this way, if this state diagram is given, I hope you'll be able to reproduce your state table. And if the state table is given, you'll be able to produce your state diagram. We'll finish our today's lecture here. We'll continue from here designing the same problems in the next class. Thank you. Feel free to contact me if you have any question.